We will now study the implementation of this sparset data structure that we conceptually just introduced. So it's implemented inside the class sparset in MiniCP. And as you can see, I didn't lie to you. There are two arrays. One is called values and one is called indexes. Okay, and this is the mapping and these are the values of the domains. And you also have the size here of the domain. You might notice that instead of a regular integer, size is stored inside what we call a state integer. For now, just consider that it's a regular integer in Java. And you can create this integer using make state integer. But the specificity of this integer is that it can restore and backtrack its value as it was before in a node of the search tree. But don't consider this for now. We will explain it a little bit later. This is related to the state manager that we will explain in a subsequent video. So in the constructor, we only initialize these two arrays. And we also initialize the size and the minimum and the maximum of the domain. Okay, and the mapping initially is the regular mapping, which was this, if you remember the previous one, it was this mapping. Okay, we consider that all the values are sorted, and so you simply need to update the indexes. You just need to initialize the indexes like this. Then comes the interesting part, which is the operations, the update operation of the sparset. A very important method that we will use is exchange positions or swap position. This operation is this one, is when you want to exchange two positions inside the value array. If you exchange these two positions, you also need to reflect it on the indexes. And as I told you, we can do it in constant time. And this is exactly what we are doing here. We are updating the indexes. So we are swapping the two values, and then we reflect the change also on the mapping from the index array like this in blue. You can also verify if a value is inside the sparset, and for that you just verify that the mapping, so index of this value that you are querying, is less than the size. Okay, if you fall before the size, you consider that the value is still inside the sparset. If you fall beyond the size, as it is the case here with this green arrow, then you say that it's not part of the set. You have the remove operation. The remove operation will simply exchange the position and then decrement the size at the end, and we will swap the position with the one at the last position at s-1, as is the current size. If you want to remove all the values, you simply set the size to 0. And this is to remove all the values less than a given specific value. This is a little bit more inefficient because you need to iterate over all the values from the minimum up to the value v that will become the upper bound of the set. And you will remove each of them one after the other. Okay? So the time complexity of this is in the order of the number of values that are still in the set. Okay, that was for the sparset. Now we also have an interface for the domain, and this is what I will just explain.